So here we have a worked example 1. There's the Z-score algorithm, and we have a new data set, the call to action button and download versus original and new. So this is an example of A/B testing. We've got a button on a website, and the button is used to download something. And there's two different versions of the button, the original version and the new version. And the question is whether the original version or the new version are more likely to result in a yes to the download action. Are they more likely to be clicked? So we look at the data before doing any calculation. We can see that the original button has about 350 out of 3,600 presses result in a download, and the new button has 451 downloads out of 3,556. So anecdotally, you might guess that the original button is slightly less effective than the new button. So let's calculate our Z-score and see the proportion for the new button, the yeses for the new button and the yeses for the original button in different proportions. So first of all, we want to get the proportion for P1, which is the yes over total for the original button, and that's 0.964. So roughly 10% of the original button presses were yes. And the proportion for the P2 is 451 over 35 is 12%, 13%, and the total population is 11%. So we feed those figures into calculation. 0.0964 minus 0.1268 over the square root of the total population by 1, total population proportion minus 1, multiplied by 1 minus the proportion, and then multiplied by 1 over n1 plus 1 over n2, and that gives us a simple z-score of minus 4.10. And we can see that our test is the z-score outside of the limits, and it is. That means we reject the null hypothesis. Okay, there is a difference between the two. So in that last work example, we calculated we worked directly from the z-score and compared it to critical values, but we can go from the z-score to a p-value using a z-score table. So taking the z-score of minus 4.10, we can then read that we can see that that's outside the critical value level, but we can read it off. So the looking at this diagram, remember that the z-score is the point on the x-axis. And if we're outside the critical value on either side, we can reject the null hypothesis. But we can also calculate directly the probability, which is the area under the curve. And if that's very small, then we can reject the null hypothesis as well. So we can read off this. We can read the z-score of the table and determine the probability. So the z-score is the column and row headings, and the probabilities, or p-value, is the data inside the table. So we're looking for a row heading of 4.10. So the highest row heading there we have is 3.4, so we'll take that. And the highest part of the highest version of 3.14 is minus 3.4 is 3.49. So we can't get to 4.1. So our table only goes up to 3.49. You can see that our p-value there is 0.0002. So if our z is higher than that, our p-value must be even lower. So we can say that our p-value is for z of minus 4.1 is less than 0.0002. And alpha is 0.05. That means the p-value is well below the alpha level. So in worked example 3, we repeat our method again, but again using one of our tried and trusted templates. So the template looks like this. We fill in the blue section with our raw data, and it calculates a p-value, a critical value, a z-score, and also a p-value, and also tells you what to do with the null hypothesis. So we fill in the data in the blue section, and first of all, the hypothesis and alpha always go in rows 4 and 5. The hypothesized difference is always 0, and the level of significance is usually 0.05. Then we fill in group 1 successes and sample size in rows 7 and 8, and group 2 successes and sample sizes in rows 10 and 11. And we get a z-score. Again, we get minus 4.1, and we get a p-value of 0. So we reject the null hypothesis.